Okay, uh, in this video, we will have a rundown on concepts under physical principles. So we will first start with the introduction. So physical principles is a branch of chemistry that deals with the interactions and transformations of materials. It focuses on the understanding of the physical properties of matter on the molecular level, the mechanism of the chemical reaction, and the principles of physics underlying all these chemical reactions. So there are several branches under this discipline, no? Uh, Physical chemistry. So we have thermodynamics. It's notoriously difficult, no? Um, in testimonies of mechanical engineering students as well as chemical engineering students. We also have electrochemistry, chemical kinetics, in other words, called reaction kinetics. We have photochemistry, spectroscopy, surface chemistry, quantum mechanics, solid state chemistry, or in other words, materials chemistry. So, there's going to be a particular focus on thermodynamics towards the end of this lecture. Na. Uh, it's probably not going to be in this video, probably in a different, in a continuous kind, because this is definitely going to be a series. One video isn't enough to cover everything. So let's move on to the brief history. So we have in the year 1752, uh, the concept of physical chemistry was coined by Mikhail Lomonosov. So he's basically a Russian guy. Um, from his lecture, a course in Through Physical Chemistry. This is just an abbreviation. In 1876, a man named Josiah Willard Gibbs wrote a paper entitled On the Equilibrium of Heterogeneous Substances. So from here, concepts were introduced, no? The Gibbs free energy, the Gibbs phase rule, and chemical potential. By 1886, Wilhelm Ostwald and Jacobus Henricus van 't Hoff founded the first scientific journal in physical chemistry. So it's basically this. In 1896, Svante Arrhenius first used physical chemistry concepts in order to calculate the extent to which increases in atmospheric CO2 results in the increase of surface temperature on Earth. So this is an important discovery now. This is how we knew that CO2, the increase in its concentration, is responsible for the increase in surface temperature now on Earth. So it's exactly what's defined in the idea of global warming. So the more CO2 emissions that we produce, we notice that climate temperatures much are getting higher now by the year. We notice it, um, especially in the Philippines. It gets hotter and hotter now, notably in certain areas too. So in 1917, Irving Langmuir's paper was published now. This is on the chemistry of oil films. If I'm not mistaken, oil films, this falls under the study of, I had it in my mind earlier. It's somewhere here. I think it's surface chemistry. Adsorption, no? That's the concept. Anyways, in 1939, uh, we have Linus Pauling's textbook, The Nature of the Chemical Bond, and its application to the elucidation of the structure of complex, what is this? Substances, no? Yeah. So, what is the importance and the role of physical chemistry? So, it's the concepts are useful for material science and molecular modeling, analysis of materials, the discovery of potential use of materials, and theory development on the properties of materials. Okay, so we're now done with the introduction. we're now moving on to the properties of gases and liquids. Um, Previously, it's basically just a preamble. You don't really have to know this in engineering. Um, these won't come out in the exams definitely, since the focus would be on the computations. But this is just to give you a brief background, no, on its history. So, matter is anything that has mass and occupies space. There are three classical states now: solid, liquid, gas. This is very basic. Um, there are other states of matter, but we don't call them classical. The fourth state is the plasma. No, this is basically hot ionized gas that consists of an equal number of positive ions and negative electrons. This results from the mixture of neutral atoms, free electrons, and charged ions. And technically, this is considered as a fluid that responds to and generates electromagnetic forces, that's EM, due to the charged particles present. So, examples are lightning, solar wind, aurora borealis, fluorescent light, neon lights, even nuclear fireball. So, if you've watched the movie Oppenheimer, you'd get what I mean. So, yes, it is hot ionized gas, so it makes sense. Uh, I think temperatures are beyond 1000 degrees Celsius, although I haven't confirmed that. It's just really hot. Um, I'm not sure if the terminology is right, but if you were within the impact of a nuclear warhead, you'd probably be vaporized. So, just to give you an idea of how hot um, plasma is. No? Okay, so for the fifth state, this is the Bose-Einstein condensate. This is a special state of matter such that atoms in a confined gas act together like a single giant particle. This is a key phrase. When you see this phrase, it's most likely the BEC, or Bose-Einstein condensate. So, a single giant particle after being cryogenically cooled to a temperature close to absolute zero. So, atoms in a BEC are in their lowest energy ground state and are unaffected by the uncertainty principle in quantum mechanics. So we have changes in matter. Two types, no? It's very basic. Physical and chemical. For physical change, it does not result to new substance formation. For chemical change, it does result to new substance formation. Uh, Reactions here are irreversible, no? If you burn paper, you cannot uh, you cannot reverse the process. Unlike when ice is melted, you can freeze it again so it becomes an ice cube. So that process is a physical change. So, properties of matter. We have intensive and extensive properties. For intensive properties, these are properties that are independent of the amount of substance or material. So, typically this is used to identify samples, no, which involve observable physical change. So, examples are loss, color, hardness, boiling and melting points, temperature, refractive index. I think molar volume also is a property of an intensive property, rather. If you see per mole per kilogram, that's intensive because it says here uh, independent on the amount of substance or material. If you, how do I say this? For example, if work is expressed in joules, then that is an extensive property because we only have joules. If it's joules per kilogram, that's the measure of specific work, or molar. I'm not sure if the terminology is right, but it's joules per mole. So if you see that, that's intensive. So yeah, if you see per, that's intensive. If you don't see that, if you just see kilogram, joules, that's extensive. Extensive properties are dependent on the amount of substance, no, or material, and they are used to determine the quantity of any substance present in a substance or material. So one example is size. We also have volume, mass, length, weight, entropy, energy. So yeah. Oh yeah. Viscosity. Where does viscosity go? Belong to rather. It belongs to intensive property. Yeah. Selected properties of matter. We have density, specific volume, compressibility, volume and shape, and molecular motion. Unfortunately, I cannot rotate this part. But basically, the idea here is that uh, for solid, it has the highest density among the three classical states of matter. But at the same time, uh, having the highest density means you have the lowest molar volume. So if gases have the lowest density, then they have the highest molar volume. That idea is particularly important um, by the time we reach the concept on real gases, no? Van der Waals equation of state, the Etrizzi-Berthelot equation of state, what else? The Virial equation of state, stuff like that. Um, because typically, using the equation of state, you would be tasked to find the molar volume, and the concept there is you will find multiple molar volumes. However, uh, the way to find the correct molar volume is to determine what is the largest among them. So having the largest molar volume, that is in theory supposed to refer to your gas. No, if the molar volume isn't the biggest, then most likely it's mixed with liquid or other substances. But for sure, it is not a pure gas. Okay, so yeah, that's just the let's call it a spoiler, no, to the next lesson. Okay, compressibility. Solid is incompressible. Gases are very compressible. Liquids are slightly. And yes, this is high school, no? High school theory. For solid, shape and volume are definite. For gas, it assumes the shape and volume of the container. For liquid, the volume is definite, but it takes the shape of the container. So yeah. What else? How about molecular motion? Solids vibrate on fixed positions. Liquids slide past one another, but for gases, they are in free motion. So yeah, we'll skip this part. This is important. Kinetic molecular theory. Uh, it's not going to be difficult to memorize this. You don't have to memorize it on the spot. Eventually, it would be easier to remember because of how many times we cite this theory in so many instances, no? Whenever we solve problems, when we compare the behavior of an ideal gas in comparison to that of a real gas. So yeah, for the first one, it's very basic. Gases are considered to be composed of minute discrete particles called molecules. So what do you mean by minute discrete? They behave separately, and so they move at different speeds. Second, the molecules in a container are in ceaseless chaotic motion, during which they collide with each other and with the container walls. So they exert pressure, no? And so ceaseless chaotic motion, this means that the kinetic energy of gases is very high. Um, the molecular collisions must involve no energy loss because of friction. In other words, these molecular collisions are considered elastic. No? And Temperature absolute is a quantity proportional to the average kinetic energy of all molecules in the system. So, yeah, this is very much true. We have to take note of that. Um, I recall the exam that I took. One of the questions were regarding this. Which of the following statements about an ideal gas is true? And everything seemed to be correct, but this one in particular was very much mentioned, no, in the kinetic molecular theory. Um, Temperature absolute is a quantity that is proportional to the average kinetic energy of all molecules in a system. Ideal gases exist at high temperature. What constitutes a high temperature? This is if the temperature is above 100 degrees Celsius or 373.15 Kelvin above. No? At relatively low pressure, the average distances between molecules are large in comparison with the molecular diameters. So, from this information, we conclude that the attractive forces between molecules are negligible. So, these attractive forces, um, they are a kind of intermolecular force. No? The other kind of force is repulsive. We'll also talk about that in the future. So yeah, right now what you have to know is that their intermolecular attraction is considered negligible. The pressure, um, low pressure, is defined as pressure below 1 atmosphere. No? So ideal gases exist at low pressure. If you see a scenario where the temperature is high and the pressure is low, you can conclude that that particular gas is an ideal, no? But in reality, it is difficult um, to it is not common, no, to see a gas that has ideal characteristics. Hence the word real gas, because it is realistic, no. But among all gases, the most likely to be ideal is helium. Okay. Okay. So for the sixth theory, since the molecules are small compared to with the distances between them, their volume may be considered negligible, no, in comparison with the total volume of the gas. So what this says is that individual molecular volumes are negligible. So okay, this is fun. The ideal gas law. This is your PV equals nRT. Definitely you've studied this already in high school, no? So it's gonna be one of the easiest things to remember. So pressure is the force applied perpendicular to the area of a surface. So we have the units of pressure here. 1 bar is 100,000 pascals. That is also equal to 100,000 newton per meter squared. Actually, there's one conversion unit here that I haven't placed. 1 atmosphere to bar. 1 atmosphere is 0.986923 bar. Yeah, sounds about right. Oh, wait, no, no, no. 1 bar to atmosphere. 1 bar is 0.986923 atmosphere. Okay? 1 atmosphere is 101,325 pascals. Pascal being Newton per meter squared, so the value is the same. No? That's the logic. 1 atmosphere is also 14.696 psia. Psia can also be rewritten as pound force per inch squared. And the same 1 atmosphere is equal to 760 millimeter mercury. That is also equal to 760 torr. Okay, so this is the volume. I'd like to conclude the video already. We'll stop here at temperature. So volume is the amount of space occupied by matter. It refers to the quantity of the 3D space enclosed by a closed surface. So we have the units of volume here. It's important, no, that you know this. 1 liter is 1000 centimeter cube. Centimeter cube is also ml, no? They have the same value. 1 cm cube is 1 ml. This is equal to 0.001 meter cube, which is equal to 1 decimeter. Another way to think of this is 1 meter cube is equal to 1000 liters. No? That's important. 1 foot cube is equal to 28.317 liters. 1 US gallon is equal to 3.7854 liters. 1 foot cube is equal to 7.481 US gallons. 1 British gallon is 1.20094 US gallons. So why am I emphasizing the conversion of each one? Where I'm coming from is there is a possibility that your professor will not allow the provision of a conversion sheet, no? A list of conversions. So these are pretty much common. So it is suggested that you memorize them. So yeah, or at least in our case, it was important for the exam for this. But in the final exam, technically, the complete coverage is supposed to be studied, but the exam was focused on more important things. No? So don't stress yourself about it. Okay, so temperature is the measure of the average kinetic energy of the molecules of a substance. So we have the conversion formulas here. But personally, I wouldn't memorize Celsius and Fahrenheit conversions because these are already in the calculator. Um, what you have to know is the conversion of Kelvin to Celsius and vice versa. Um, so it's this one, plus 273.15, if you want Kelvin to be in Celsius. And for Rankine, to Fahrenheit, from Fahrenheit to Rankine rather, Celsius to Kelvin is Celsius plus 273.15. Fahrenheit to Rankine is Fahrenheit plus 459.67. You have to memorize this exact number. Okay, so we'll skip this part. Okay, that's it for this video. We'll continue. No?